In our last video, we looked at thermodynamics of organic reactions, and in this one, we will be looking at kinetics. We saw that thermodynamics gives us information on whether a reaction is favorable or whether a reaction is spontaneous or not. With kinetics, the focus is on determining the rate of the reaction. So how quickly does a reaction proceed? We're going to see some examples where a reaction might be favorable, but it is very slow. So the information you get from kinetics really complements the information that you get from thermodynamics to give you a more complete understanding of a reaction. One of the major goals of kinetics would be to determine a rate law. This gives specific information about the rate of the reaction and how that depends on the concentration of the different reactants. So let's come back to the reaction we looked at earlier where A reacts with B to form C and D. Now earlier we were focusing on the fact that this was a reaction at equilibrium, so it was important to use the equilibrium arrow. In this case, because we are focusing on the kinetics, we don't care about the reaction at equilibrium, we care about only the reaction in the forward direction. So it's okay to use either type of arrow, although when we're talking about equilibrium, it's more important to specify using the equilibrium arrows. Recall when we talked about equilibrium, we had an equilibrium expression where the equilibrium constant K is equal to the concentration of the products where their exponents are their coefficients divided by the concentration of the reactants. Well, for a rate law, now we are looking at the rate is equal to a rate constant K, now this is a lowercase k, times the concentration of A to the X times the concentration of B to the Y. Please be careful to use a lowercase k for the rate constant and a capital K for the equilibrium constant, and please also make it clear which is which. While for the equilibrium expression, the coefficients became the exponents, for the rate law, the coefficients are not automatically the exponents, and these exponents have to be determined experimentally. But the rate law is given in terms of the concentrations of the reactants. Now, how would you go about determining the rate law? So as a very simple example, let's say we are looking at the concentration of A and the concentration of B as we set up our reaction, and then we are able to measure the rate of the reaction. What's the change in reactants over time, or what's the change in products over time? Let's say we start out with 1 mole of A and 1 mole of B, and we measure a rate of 10 millimoles per minute. Now we can repeat the reaction, and maybe this time we double the concentration of A and hold the concentration of B constant, and what we measure is a rate of 20 millimoles per minute. Well, that tells us that the rate is proportional to the concentration of A. We could go back to the original concentration of A and double the concentration of B, and maybe this time we measure a rate of 40 millimoles per minute. Well, this tells us that the rate for this made-up reaction is proportional to the concentration of B squared. So for this particular reaction, we could say that the rate is equal to a rate constant K times the concentration of A times the concentration of B squared. Now, obviously, you have to carry out more than just 3 reactions, but this is just an example. Once the rate law is determined, this is only the beginning of the investigation. There's still a lot more work to be done to be able to understand why the rate depends on the concentration in this way And therefore, what is the mechanism of the reaction? How does the reaction actually occur? So we saw an example of how a chemist would determine the rate law experimentally, but what is it that actually really determines the rate law? What is it that causes the rate law? So both physically or molecularly, what is responsible? So there are a few things that we need to consider. One of them is the reaction mechanism. So the mechanism is a detailed description of any reaction. So this will give us information on whether the reaction occurs in a single step or whether there are multiple steps, multiple elementary steps. Are there intermediates? For example, when we talked about A plus B reacting to form C plus D, it's possible that this occurs in a single step, and that would be a single elementary step. Or it could happen that maybe A plus B react to form E, and then E further reacts to form C plus D. So the overall reaction is A plus B reacts to form C plus D, but we also have an intermediate, E. So in this case, we have two elementary steps that make up the overall reaction. Now, an elementary step is any reaction step that has a single transition state. And the transition state is the structure in a reaction step that has the maximum energy. So this is the highest energy. So a transition state is unstable and it can't be isolated. And typically it can't be observed. But the transition state is another important concept, and we're going to talk more about that. We also have to consider the activation energy. So the activation energy is the difference in energy between the reactants and the transition state. So transition state, I use TS. So the activation energy is the difference in energy between the reactants and the transition state in any elementary step. So I usually use EACT for activation energy. The textbook uses delta G double dagger. So the delta G is the Gibbs free energy, and the double dagger refers to the transition state. I would say that I would try to use a delta G double dagger, but habit, I'm just going to use EACT. So just be aware of that. One thing that I don't like in the book is that they talk about both the delta G double dagger for an individual step, and they also talk about the delta G double dagger overall. But I don't want us to worry about delta G overall because we are going to focus on the rate determining step. So there are several questions in the textbook that ask for the delta G double dagger and the delta G double dagger overall. So just ignore that part of the question. So we are going to focus on the rate determining step, which is the slow step in a reaction. So it has the largest activation energy of any of the elementary steps. And so this actually determines the overall rate of the reaction. So we are going to look at many examples of reactions where we try to understand the mechanism. We are going to look at energy diagrams that help us to represent the transition state, and the activation energy help us to determine the rate determining step. So this has just been an introduction to kinetics or a refresher on kinetics if you did cover it in general chemistry. And we are going to talk a lot more about both thermodynamics and kinetics as we continue, especially as we look at energy diagrams.